Okay, so now I'm going to finish up this problem about the scientific instruments that are falling through the sky, and the potential energy is decreasing as it falls, and the kinetic energy isn't increasing as quickly because some of that energy is getting sucked away into heat. So I ended with saying that really what I would need to do is I need to find the difference between how quickly the potential energy changes and how quickly the kinetic energy changes. If they were equal, then no heat would be generated. If they're not equal, the difference is how much is going to someplace else. Okay, so we know potential energy is mass times gravity times height. We know kinetic energy is 1/2 mv squared. So this comes down to figuring out expressions for those two things and taking the derivative and then subtracting them. Okay, so let me simplify this a little bit. I don't need to go all the way to finding a function for the position and then taking the derivative of that, because one, that would be difficult. I would need to do the integral I just did again to find a position function and then take the time derivative of that. But let's think about this. Let's not waste our work here. The time derivative of mass times gravity times height, well, the mass isn't changing, and the strength of gravity isn't really changing. That's equal to m times g times the derivative of the height. Okay, well, the derivative of the height is the velocity function. So that's really the same thing as mass times gravity times the velocity as a function of time. That's how quickly the potential energy is changing. And I already have a function that I've worked out for the velocity. That was the purpose of this integral right here. So I'm just going to rewrite that a little bit as I'm going to move that negative sign inside and get g tau 1 minus e to the minus t over tau. That's the same thing, just moving the negative sign inside. That's how quickly the potential energy is changing. So that's multiplying that by the mg times g tau 1 minus e to the minus t over tau. And that gives me mg squared tau times 1 minus e to the minus t over tau. That's how fast the potential energy is changing. Now I want to do the same kind of thing for the velocity. But here I need to look at, okay, I want the derivative of 1/2 mv squared. Well, the mass doesn't depend on the velocity, on the time, but the velocity does. So I need to do a chain rule thing. So the 2 comes out front, and you get 2 times 1/2 times mv times dv dt. Chain rule. Okay, well, the 2 and the 1/2 cancel out, and you get mv dv dt. Well, I already know the velocity function. It's this same thing right here. Let me just kind of circle that. That's the velocity function. Velocity function. And I already know what dv dt is. That's the acceleration. We started with that. The acceleration is that ge to the minus t over tau function. Okay, so I've got both of those things already, and I can just put them down to figure out how quickly the kinetic energy is changing. So we've got m times g tau 1 minus e to the minus t over tau. And at this point, I'm going to make my screen a little bit bigger. There we go. Give myself some more room. Times the acceleration, which way back up here at the beginning, ge to the minus t over tau. Ge to the minus t over tau. And rearranging that a little bit, you get mg squared tau. That's nice. It's got those same prefactors. And then if I move that e to the minus t over tau inside, you get e to the minus t over tau minus e to the minus 2t over tau. because if you multiply those two exponentials together, you add up the exponents. Okay, so we're almost there. This one is the rate of change of the potential energy. This one is the rate of change of the kinetic energy. If we were in friction-free world, they'd be equal to each other, but they're not, so I'm going to subtract them. And the difference will be how fast heat is being generated. Okay, let me switch to black now. So I'm going to do the difference between those two functions, mg squared tau. And I noticed right off the bat that I've got that same prefactor. So I'm going to pull that out right away. And then make a really big 1 minus e to the minus t over tau. That's coming from the left side. And then I've got this thing minus e to the minus t over tau plus e to the minus 2t over tau. Those two pieces are coming from there. And the reason those signs flipped is because I'm subtracting. That minus right there goes there. Okay. Now I'm going to look at this and see if there's any way I can simplify it, because I've got a bunch of different exponential factors there. And I notice this is of the form of 1 minus 2x plus x squared. I've got two things that are the same and one thing that is squared. So that suggests 1 minus x squared as a factored form if x equals e to the minus t over tau. Just to say all that explicitly. Basically, I'm going to factor that expression with the exponentials. And I get mg squared tau times 1 minus e to the minus t over tau squared. That's the difference between the two rates. That's how quickly heat is being generated. That's the answer I'm looking for the first part of the problem. And you can further see in here how we got the answer we got before for in the long time limit, what's going to happen? Well, in the long time limit, this second term in here, the exponential, goes to 0 because e to the minus big number is 0. And then the only thing that matters is the mg squared. Therefore, in the long time limit, the rate of change of the rate at which heat is generated is mg squared tau, whatever that is, and you can plug those numbers in. So there we go. That is the whole problem. Key is thinking about how fast does the kinetic energy change, how fast does the potential energy change, what should the relationship between those be if there wasn't any friction, and what is it in this case when there is air resistance, and there you go.